Good morning. This is Gerald Eigen from the University of Bergen, and I report on measurements of the polarization correlations of the two-photon system produced in positron electron annihilation. Okay, so I start with the outline. After a short introduction, I discuss the measurement principle, then the measurement setup, the polarization correlation and measured observables, say something about simulations, then about the analysis requirement, data selection, and systematic effects. Then I'll present results. I show some comparison with other experiments. I show a test of Bell's inequality before I conclude. So in the early 1970s, two experiments were conducted that measured the polarization correlation of the two photons from electron-positron annihilation. The experiment by Kasday, Ullman, and Wu at Columbia University measured a polarization correlation that confirmed the quantum mechanical expectation. There was a second experiment conducted by Ferracci et al. At Catania University in 1974 that measured a value that was 30% lower than the quantum mechanical expectation. The discrepancy could not be explained. Therefore, Klaus Meisenheimer and myself, we were two diploma students under the supervision of Professor Runge, built a new experiment for measuring the polarization correlation at the University of Freiburg in Germany. The experiment was conducted like a modern high-energy physics experiment with respect to data taking, analysis, and simulation. So the measurement principle, positrons from a source, a copper-64 source, annihilate with electrons in the conduction band. And this happens typically in an S state. And so it produces two nearly back-to-back photons. If you look at them, the full width at half maximum is 5.9 milliradian. This is shown in the middle plot at the bottom here. The two photons are either left-handed or right-handed polarized. So the state vector in terms of momentum k sub I and polarization epsilon sub I, which could be right-handed or left-handed, is given by psi is 1 over square root of 2, k1 r1, k2 r2, minus k1 l1 and k2 l2. And this can be expressed in terms of linear polarization. And then we get psi is 1 over square root of 2, k1 x1, k2 y2, minus k1 y1 and k2 x2. Now the polarization is detected via Compton scattering, with primed observable are those of the scattered photons. And this is for I equals 1 or 2. And then here is the cross-section for Compton scattering. And you can see that it depends on the polarization of the photons represented by the vector epsilon sub I and epsilon prime sub I. The two pictures on the bottom show the two positions, either right-handed or left-handed polarization. The probability that a photon polarized in the x direction is scattered under the angles theta and phi is given by this formula p sub dp sub I, 1 over square root of 2 pi, 1 over 2 pi, f of theta sub I, 1 minus m theta sub I, cosine 2 phi sub I d omega, where the f of theta is given by 1 over the normalization constant, and then k prime over k squared times ki over ki prime plus ki prime over k minus sine squared theta. And this term represents the polarization. And then the function m of theta is given by sine squared theta divided by k sub I over k sub I prime plus k sub I prime over k sub I minus sine squared theta. So the function f of theta is proportional to the differential cross-section of unpolarized photons, whereas the function m of theta is a theta-dependent amplitude that describes the strength of the phi dependence and therefore the polarization sensitivity. On the plot on the right-hand side, you see two distributions. The upper one corresponds to Thomson scattering, whereas the lower one represents Compton scattering. And so you see that this function has the minimum close to theta equals 82 degrees. But as we'll see, this has the largest sensitivity for the polarization measurement. So the maximum polarization sensitivity, as I said, is for theta equals 82 degrees. And we get a value which is 0.691, whereas the ratio of the function f at 82 degrees and 0 degrees is only about 0.2. So it's nearly at the minimum. Now for fixed theta, the p over the omega becomes maximum if the initial polarization is orthogonal to the scattering plane. This means that phi is equal to 90 degrees, whereas the minimum occurs at phi equals 0. And that's represented here in these two diagrams at the bottom. And you can see here the function m of theta as a function of theta. The top curve is for Thomson scattering. You see at 90 degrees, it peaks at nearly 1, whereas for Compton scattering, it's shifted a little lower to 82 degrees, and it's much less than 1. I'm sorry. So the analyzing power is a measure for the polarization sensitivity of a polarimeter. Epsilon p is the difference of the maximum polarization measurement minus the minimum polarization measurement normalized to the sum. And so p max is the maximum of the p over the omega if epsilon is parallel to the polarimeter axis, and p min is the minimum of the p over the omega if epsilon is orthogonal to the polarimeter axis. And so for a Compton polarimeter, we get that epsilon Cp can be factorized in the function capital M of theta and d theta times a function n, which just depends on delta phi. And so the plot on the left-hand side shows the function n of delta theta as a function of delta theta. And you see it drops. So if delta phi increases, and typically we measure at 10 degrees, you don't get the value of 1, you get something lower. And the right-hand side shows the function m of theta delta theta. And you see the peak again is at 82 degrees for theta. It's plotted as a function of theta, but it's shown for different intervals of delta theta because you have a finite opening. And we typically measure at 14 degrees. So we measure at this value here. And these functions are basically, they're integrals of the function f of theta times m of theta times sine theta d theta, and it's normalized over the rest without the function m. And the function n of delta phi is integral over cosine 2 phi d phi over the integral over d phi. And this gives sine 2 delta phi over 2 times delta phi. Now, one word on detection efficiency. The detection efficiency is defined as a number of detected particles over the number of particles hitting the polarimeter. So if you have an ideal polarimeter, eta is equal to 1. For optical polarimeters, eta is of the order of 30%. And for our Compton polarimeter, there are several factors that enter. There's first, eta sub s, the scattering probability in the scatter. That's of the order of 0.3, obtained from Monte Carlo simulations. Then we have the probability to record a signal in the detector. This is about 0.877, also determined from Monte Carlo. Then we have delta S, that's the detection limit of the scatterer. That's about 0.81, and it depends on the discriminator threshold in recording the signals from the scatterer. And delta D is a detection limit on the detector. This is about 1, and it depends on the discriminator threshold. And then we have a function which f of theta and delta omega, and this is just the integral of the function f of theta times the omega over the interval delta omega. So for a realistic arrangement, theta equals 82 degrees, delta theta equals 14 degrees, and delta phi equals 10 degrees, eta Cp is about 1.46 times 10 to minus 3, so it's rather small. Now I want to say a word on the quantum mechanical correlation of the two-photon system. The probability that two photons represented by the state psi are scattered under the angles theta 1 and theta 2, and the azimuth angles phi 1 and phi 2 is given by dp12 is 1 over 4 pi f of theta 1, f of theta 2 times 1 minus m of theta 1, m of theta 2 times cosine 2 phi 1 minus phi 2 times delta omega 1 and delta omega 2. The flight directions of the two photons after scattering are correlated with respect to the azimuth angles with a strength of m of theta 1 and m of theta 2, and the maximum value here is 0.478. The two scattering angles are completely independent, and f of theta 1 and f of theta 2 denote the probability for scattering two arbitrary polarized photons under the angles theta 1 and theta 2. So now I come to the experimental setup, which is shown on the graph on the right-hand side. We have a copper 64 source, which sits inside a collimator. It emits two photons back to back. And then we have two polarimeters on each side, which consist of a scatterer and a detector. So the scatterer is a plastic scintillator, which is read out by a light guide and a photomultiplier. And the detector is a sodium iodide crystal, which is also read out by a photomultiplier. And it has a lead shield in front of it to define the acceptance of the detector. And so our optimal scattering angle here will be 82 degrees. And then we record 4 coincidences. We record the coincidence between the two scatterers, called N2. Then between two scatterers and one detector, that's N1, N31. And then on the other side, it's N32. And then finally, the fourfold coincidence of all 4 detectors. And that one depends on the azimuth angles phi 1 and phi 2. So here are some pictures of the experiment, which was conducted in Freiburg. On the right-hand side, you see what we did is we placed the symmetry axis of the experiments parallel to G. Then this triangle in the middle shows the source and the collimator. And then the two triangles on top and bottom show the polarimeters. So here you can see the scatterer. And then here you see part of the detector. So there's a close-up view on the left-hand side. So you see the scatterer, you see the collimator, and then the detector, and you see the lead shield, which shows this opening angle. We use different kind of scatterers. So here you see there's one here with a layout of a conical scatterer. And in the beginning we had a tin source, but it turned out that we got too many accidental coincidences and we removed it. And then here you can see is a sketch of the arrangement in the phi direction and in the polar angle direction, showing the opening which defines our acceptance. Then we defined a polarization correlation, R of theta 1 and R of theta 2, in terms of coincidence rates to reduce systematic uncertainties from the source intensity, alignment, and calibration. So what we do is we take the fourfold coincidence and normalize it to the twofold coincidence. And this ratio is then normalized to normalize threefold coincidence, N31 over N2 and N32 over N2. So what we get is basically the fourfold coincidence times the twofold coincidence divided by the product of the threefold coincidence. In the laboratory, there's no preferred polarization direction, which means that the threefold coincidence are isotropic in phi 1 and phi 2. And the angular dependence comes from from the fourfold coincidence, which depends on phi 1 and phi 2. And the dependence is given by a function which has a factor A, times 1 minus beta times cosine 2 phi 1 minus phi 2. And beta is basically the correlation parameter we want to measure. And A should be typical of the order of 1. If it deviates of 1, that means that we have some non-perfect alignment and some other small systematic effects. If we had uncorrelated photons, then R would be identical to 1. Now, in a quantum mechanical system, beta is given by, it's less equals to the product of m theta 1 times m theta 2, and this is less than 0.478. Now, there are some effects that influence this correlation rate, R phi 1, phi 2. And these parameters are, it depends on the analyzing power of the polarimeter. It depends on changes of the two-photon quantum state. And it depends on a bunch of backgrounds like accidental coincidence, uncorrelated coincident photons that come from the source. That copper-64 is a 1.3 MeV gamma, which could, produce some accidental coincidence. Then secondary scatters in the light guide, which in the lead shield, which also give you events which are background. And then events could double scatter in the scintillator. And as I will show you, double scattering reduces beta by a large factor. Then there may be some other systematic effect that change the analyzing power or change backgrounds. And one is, for example, the misalignment of scatterers. Now, the measured observables we take are the following. We determine the polarization correlation parameter, called beta experimental, from R phi 1 and phi 2 by measuring at different values of phi 1 minus phi 2. And we have done 4 data sets. And in these 4 data sets, we vary parameters in the following way. We have 2 sets where in one hand we had a cylindrical scatterer, and the others we had conical scatterer. We measure at 82 degrees and at a distance source from the scatterer of 16 centimeters. Then we vary the scattering angle. I showed you that 82 degrees is the optimal one, but we also measured at 68 degrees with the same distance. And then we vary the distance source as scatterer from 16 to 42 centimeters. Because in this case, the 2 photons may be space-like, and there should be no signals able to be transferred back so that they know any information. For each measurement, we record the following observables. As I said, we record the 4 coincidence rates, N2, N31, N32, and N4. And also we record the corresponding accidental rates. We call A1, A2, A31, A32, and A4. Single rates and the scatterers and detectors. These are the individual rates in each of these, in the scatter 1, scatter 2, detector 1, detector 2. We also measure the response times in each of these 4 detectors. And we also look at a TDC spectrum for all 3-fold and 4-fold coincidences. For 3-fold and 4-fold coincidences, we further measure the energies in each of the detectors. So in scatter 1, scatter 2, detector 1, and detector 2. And then for coincidences, the response times have to be consistent within the errors. And for the coincidences, the energy of the electron and the photon has to be 511 keV within errors, which corresponds to the energy measured in the scatter and the energy measured in the detector. We wrote a very sophisticated Monte Carlo program, which had the goal to determine the quantum mechanical expectation value for the polarization correlation parameter beta QM for all 4 data sets. And we have simulated the experiment in very great detail. We simulate the form and position of the source and all the effects inside, the effect of the collimator, the shape and position of the scatterers, the opening of the lead slits, and the absorption of the sodium iodide detectors. And so with this, we can determine the dependence of beta QM on theta, as well as on the acceptance delta theta and delta phi. We can determine the effect of multiple scattering in the scatterer on which it has on the beta QM, the determination of efficiencies of the scatters and detectors, and the determination of energy distribution and ratio of coincidence rates. We did a event-by-event simulation. However, the beta QM cannot be determined directly from DP1 and 2, because for the generation of Compton scattering, we need to make concrete assumptions about the polarization state of the two-photon system. So if you look at a pure state, psi, which is represented by the density matrix, psi times phi, which is equal to 1/2 times x1, y2, y2, x1, plus y1, x2, x2, y1, plus x1, y2, sorry, x2, y1, plus y1, x2, y2, x1. And this cannot be factorized into individual polarization states, which means that dp12 cannot be written as a product of dp1 and dp2. However, there are two possibilities to determine the quantum mechanical expectation value. Okay, the first one is we can determine the analyzing power of each Compton polarimeter, and then just determine it from the function r phi1 and phi2. And the second is we can determine the expectation value of a symmetric mixture, which is shown on the right-hand side. So phi is 1 over square root of 2, x1, y2 plus y1, x2. And so in case of the symmetric mixture, we get that dp1, 2, is 1 over 4 pi f of theta 1, f of theta 2, times 1 minus 1/2 m of theta 1, m of theta 2, times cosine 2 phi 1 minus phi 2. So you see we get the same shape as for dp12, except for an additional factor of 1/2 in front of m theta 1 and m theta 2. What we do is we use both methods to simulate the quantum mechanical expectation value for the 4 data sets. And for the first method, beta QM is just the product of the 2 analyzing powers determined from Monte Carlo. And for the symmetric mixture, we get r phi1, phi2 is a times 1 minus b, depending on all these parameters, times cosine 2 phi 1 minus phi 2. And then we determine from a fit this parameter beta, and then the value is given by 2 times this value beta. So the analysis requirements are the following. We introduce 4 selection categories, which we call 0, which means 0 is basically the raw number of events for all the measured coincidences with no additional cuts. Then category T introduces a requirement on the time selection. So for the time between the 2 scatterers has to be less than 1.6 nanoseconds. Then for the 3-fold coincidence, N3-1, the time between detector 1 and scatter 1 has to be less than 4.6 nanoseconds. And similarly for the N3-2, the time between detector 2 and scatter 2 has to be less than 3.6 nanoseconds. The third category is we make a requirement energy sums, namely that the energy sum of scatter 1 and detector 1 lies between 370 and 650 keV. And for the other system, between 385 and 635. And the final cut is that we make a requirement of the energies detected in the detectors, namely that between 200 and 325 for detector 1 and 195 and 320 keV for detector 2. We apply all these cuts successively. And on the right-hand plot, I show you the spectrum measured in the detector. Between the 2 bars is basically what we measure as a signal. But then you see we get also energies on the upper plot, on the upper side and on the lower side. And these come from different effects. For example, here you can see that energies here come from that the scatter scatters in the lead shield before it is detected in the detector. Or we have multiple scattering that, you have a large scattering and then it goes into the detector. Whereas in this region here, it goes directly into the detector. And so you see also the spectrum after applying all these cuts, we basically get rid of all these tails on the left and right-hand side, and we just lose a few events in the signal region, which is shown here for category E, the shaded histogram. Here are some results from the simulation, which shows you that multiple scattering has a large effect. On the left-hand side, you just see the function beta QM as a function of the angle theta for single scattered photons. And so you see that the different curves show the different cuts, and you see that basically they have no effect if you only had single scattered photons. This changes if we allow multiple scattering, including and single scattering. And then you see now, if I measure events in category 0, you get here the solid points. And so you see that here the function is reduced. We get values here of 3.5 instead of above 4. And then after applying cuts, you see that the value increases, but it never gets to that, what single scattered photons would produce. And so it's very important to arrange the experiment in such a way that you minimize the multiple scattering, and that with these selection criteria, you remove events which have double scattered photons inside. Here are similar plots of beta QM as a function of delta theta and delta phi. And on the left-hand side, again, is only for single scattering. You see it doesn't make much difference. Of course, if you increase the window in delta theta, then the quantum mechanical correlation goes down. The same is true, and it is shown here for different values of delta theta. And so if you increase delta theta, it goes down too. But then if you allow with multiple scattering, then these curves get reduced. So the solid points are again the ones where we apply no cuts, and then the open circles are when we apply the energy requirements, and then it moves a little bit up. So it's very, we have to know exactly what values of delta theta and delta phi we use in our measurements in order to determine beta quantum mechanics. Here's another plot which shows just the multiple scattering by itself as a function of theta and delta theta. And you see that, before we saw values above 4.4, and you see here we get about a factor 2 lower values for beta multiple scattering. So multiple scattering basically destroys the polarization correlation, and so it has to be limited. So here we now show for data set 2 the results we get. This is the function R phi 1, RR21 from phi 1, phi 2, which has this form of 1 plus beta times cosine 2 phi 1 minus phi 2. You see it shows a nice correlation. And then we can determine beta experimental from these values. And it's shown for all the 4 categories, 0, T, S, and E. And then here we have the fit results. So for 0, you see we get 0.37. And then with the next cut on the timing, it goes up to 0.381, with some energy cut to 0.397. And then with the energy cut in addition on the detectors, this goes to 0.415. So basically here, a lot of multiple scattering events have been removed. And so we get close to the value you would get for just single scattering. There are a bunch of systematic effects. As I already said, multiple scattering is one of the largest. So the amount of double scattering, fourfold coincidences is about 17.8% for category 0. And then with all the criteria, including the energy cut, it gets reduced to 10%. Then we have accidental coincidences. This is rather small for the categories D, S, and E. For example, A4 over N4 is 0.39%. For category T, it goes to 0.15% for category S and less than 0.5% for category E. And then the effect on beta QM is negligible. Then we have coincidence with the 1.34 MeV photon from the copper 64 source. And so here, the rate with the 1.34 over N31 is less than 6 times 10 to the minus 4, which also means that actually we can neglect it on the determination of beta QM. Then there are secondary scatterings in other parts of the detector, like in the shields or in light guides or so. And this category actually gets completely removed with the sum criteria. We also have a geometric correlation, which we actually can determine from our 2 simulation methods, because the first method doesn't include the geometric correlation, whereas the second one does. And so if we compare the results, we can determine a factor, and this correction factor is very small. It's a few percent. Then there are other systematic errors. The azimuth angle scattering is better than 1 degree. So delta phi is plus minus 2 degrees, and then delta beta over beta is less than 1%. And deviations from rotation symmetry yield a negligible error on beta. So here's a table which shows all our results. It's shown on the 3rd column for categories 0, T, S, and E. I showed you the results for data set 2 already. You see for data set 1, we get very similar results. For data set 3, they're lower because the scattering angle here is 68 degrees and we expect lower values. And for data set 4, we get similar results to data set 2. Here we only change the distance from the source to the scatterer. And so, as I said, the correction factor is 1.026 with an error of 0.0323. And so this is consistent with 1. And so then on the 4th column, we have the results from the simulation, which actually are in excellent agreement with the measurements, so that the ratio of the measurement over the simulation is of the order of 1, which is shown in the 5th column. At least you see when we apply the cuts T, S, and E, it's always consistent with 1. Only for 0, it's a little lower. What we then do in order to compare our results with those of other experiments, we take this ratio, beta experimental over beta quantum mechanic, and multiply it then by the maximum value of 0.7478. And so in the last column, this result is shown, and these results we then display on the next page. So here we have the 4 data sets, and we show the results for the 4 categories. So 0 is the first for time requirement, the second, the sum energy is the third, and then the final energy in the detector is the 4th. And what you see is that for categories S and E, all the results are in good agreement with the quantum mechanics. For 0, they're a little lower, but they're within 2 standard deviations. And for T, they're basically consistent with the quantum mechanics already. So what we then do is, and since these were done under different conditions, we can actually determine an average of all the 4 data sets. And the results are shown here on the left-hand side at the bottom. So we get beta 0 is 0.454. With timing, it goes up to 0.463, with the sum energy to 0.483, and then with the energy requirement to 0.479. So this means that all data sets agree with quantum mechanics better than 2 standard deviations. Now I have a few comments. So if you look at the averages, beta 0 for the category 0. This is actually 5 plus minus 1.9% below the quantum mechanical value. And for beta t, it's 3.2 plus minus 2% below the quantum mechanical value. So the systematic deviation is caused by events that are scattered in other parts of the detector. This is an effect we could not consider in the Monte Carlo. Now, assuming that the azimuth angle distribution for such events is similar to that of multiple scattered events, we can estimate this. And so we can estimate this beta for these events by 1 plus 2 times the number of photons that are scattered a second time outside the scatterer, times 1 minus the polarization sensitivity for multiple scattered events over that of single scattered events, times beta for single scattered events. And so we find a value of 0.459, which is consistent with the corrected averages of beta 0 and beta t. But what I should say is that when we apply the energy sum, this removes this background completely. Now, for categories S and E, the deviation from quantum mechanics is 1 plus minus 2% for S and 0.2 plus minus 2.3% for E. I should also say that mixing of the first kind is clearly ruled out, as well as a value of 0.478 divided by square root of 2. So now I come to comparison with the other experiment. So by the time we completed our results, we had 4 experiments. Besides Casday and Ferracci, we found that there was an experiment done by Langhoff in 1960 already. And then another Italian had performed another measurement. And so here I have all the parameters given by these different experiments. And what we try to do is we try to simulate their setups as well as possible, given the information in the papers. For some of these experiments, the documentation was not too well, but we tried our best. So here is the comparison then. We classified again according to the categories 0, T, S, and E. And these different experiments actually perform different types of analyses. For example, for Ferracci et al., they did not make any additional cuts. They just plotted their raw data. They had a pretty thick scatterer. What we show here in this plot are basically 3 different types of values. We show the raw data measurement, which is the open circle. Then the stars represent the measurements done by the experiments themselves, applying some corrections. And then the full circles are the measurements applied by our Monte Carlo corrections. And so you see the Ferracci experiments, they didn't only do category 0, they didn't apply any other cuts. And with their correction, they get something which is like the quantum mechanical expectation value divided by square root of 2. Whereas if we apply our correction, the values are shifted up. They're not exactly at the quantum mechanical value because we couldn't correct for all the effects, as I said before. So we just corrected for multiple scattering, and they get very close. Then we have the experiment by Casday et al. These are the blue measurements. They did not plot the raw data, and they just showed for the some energy and the energy. And you see the raw data are somewhere here, and their corrections already are in good agreement with quantum mechanics, and this is confirmed by our corrections. Then the experiment by Langhoff, the same thing. Here are the raw measurements. The corrections they made are already agreeing with quantum mechanics, and this is confirmed by our corrections. And then for the Bruno experiment, they only applied the some energy cut, not the final energy cut. Here are the raw measurements, but also their corrections give an agreement with quantum mechanics. And this is confirmed by our corrections. So what we can conclude then is Langehoff, Bruno, and Kessler agree well with quantum mechanics. And I should say, I forgot to say, the red points are our results I showed you before. Then Faraci, with their own correction, find a value that's consistent with quantum mechanics over square root of 2. But Faraci, with our correction, is closer to quantum mechanics. But since there's no energy and time constraint, the correction is still too small. Okay, then let me come to the test of Bell's inequality. Bell formulated the following equality. So you have this correlation function, P of A and B, which is an expectation value of an observable A that measures parameter A and an observable B that measures parameter B. And then by the selection of 4 appropriate parameters, A, B, A prime, and B prime, you can formulate this equation, which should be satisfied. So we have the absolute value of PAB minus plus PAB prime, and then the absolute value of PA prime B minus plus PA prime B prime should be less equal to 0. Now for a real experiment, the quantum mechanical correlation is given by PQM phi 1 and phi 2, which is 1 minus delta omega over 4 pi. Then we have the probability that we have a twofold coincidence, it's defined here, times the detection efficiency, 2 minus twice minus the detection efficiency times 1 minus epsilon square, cosine 2 phi 1 minus phi 2. And so using the 4 values, 2 phi 1 to be pi over 4, 3 pi over 4, 0, and minus pi over 2, we then get that FQM minus 2 is equal to 2 times delta omega over 2 pi. P2, detection efficiency times 1 minus epsilon squared times square root of 2 minus 2 less equals 0. So this means the equation is violated if this factor is larger than 2. If you look at the real experiment, detection efficiency times 1 plus epsilon squared times square root of 2 is less equal to 1.68 times the detection efficiency, and this is much smaller than 2. So for that reason, if you plot here the detection efficiency versus epsilon square, we would expect violation here. However, the measurements from positron annihilation, they're all down below here. And even there were some optical experiments which have very good polarization power, which is close to 1. But the detection efficiency, of course, is also small. So they're basically in this range here. So none of the present experiments actually gets close to the violation limit. So therefore, we cannot speak of violation of Bell's inequality. This brings me to my conclusion. We measured the polarization correlation of the 2-photon system from positron-electron annihilation. We varied the shape of the scatterer, scattering angle, and distance source scatterer. We simulated the quantum mechanical expectation value with a very sophisticated Monte Carlo program. All results are in good agreement with the quantum mechanical expectation value. We simulated the quantum mechanical expectation value of 4 other experiments. The measurements either agree rather well or are consistent with the quantum mechanical expectation value. The discrepancy of Faraci with the quantum mechanical expectation value they quote is due to the neglect of multiple scattering, which reduces the polarization power of the polarimeters and needs to be corrected for. Thank you.
Gerald, congratulations. Your lecture is absolutely magnificent. If I can say in Latin, Lactio Magistralis. I would like to confirm that I believe that Bell's inequality is indeed correct. I believe in quantum mechanics for electromagnetic.
No, it is correct. We talked with Bell about it.
Yes.
The problem is some of the people claim they have violated Bell's inequality.
No.
That's what Bell told us. they correct for the detection efficiency, and you're not allowed to do that. And you said, if you do that, it's not his inequality anymore.
Absolutely.
It's their own inequality.
No. I provided myself an alternative proof, which is by using even different mathematics that turns out to be absolutely correct under the assumption of quantum mechanics, namely for electromagnetic interactions. The doubts that we have now, but those are doubts, is whether what happened under strong, whether the additional electromagnetic and strong interaction, because we have not yet achieved an explicit representation of what the strong interactions are. So we have, we're at the zero level. So this is the only, in other words, inside the proton, inside the nucleus, this is the open issue. But for any mutual distance, which is over the 10 to the minus 13 centimeter, as you nicely, very nicely stated, that the Bell's inequality, they cannot be stated to be wrong. Absolutely, it is correct and it is exact. On the strong interaction, we may say it could be inapplicable, but not violated, absolutely not violated. This is my formal position that I've stated in my papers, and with the understanding that we don't know. My own personal conclusion, but Gerard, I beg you, this is just friendly. My personal conclusion is that, under electromagnetic interaction, we have a real physics beautifully presented by you, which is correct, axiomatically correct, experimentally verified, as while to be real scientists, rather than political scientists, when we add the strong interaction, we have to say at this moment that we do not know. Simply, we are not in a position to make a final statement. Quantum mechanics has been unable to represent the data of the deuteron, let alone big nuclei. So we have, the issue.
I know Helmut Quint once tried to give a talk on lambdas, EPR with lambdas. But the problem may be they're not relativistic, they're slow. And then you don't have the condition of space-like separation. So you could have electromagnetic signals being, transmitted while you measure them. So I don't know whether that's an issue or not.
It is an issue. Everything is an issue. We know so little, but that's the challenge. The conference is attracting a huge interest, much more than I expected, because it touches to the edge of our knowledge. And also.
Okay, very good. I'm looking forward to the conference.